In 2024, JWST pointed at Alpha Centauri A, our nearest Sun-like star, and saw something wild. A cold Saturn-size planet glowing in the habitable zone, just 4.37 light-years away. In 2025, JWST looked again, and the planet was gone. In this video, we're diving into what JWST actually saw, why a disappearing world 25.6 trillion miles or 41.2 trillion kilometers away has scientists on edge, and how the next few years could confirm our first real gas giant neighbour, or prove it was all an incredibly convincing ghost. Let's lay out the basics very clearly. Alpha Centauri A is a star. A lot like our Sun, a bit bigger, a bit brighter, sitting about 4.37 light-years away, roughly 25.6 trillion miles. That's about 41.2 trillion kilometers. In August 2024, JWST turned its 21-foot or 6.5-meter mirror toward that star, used its mid-infrared camera with a special mask to block the glare, and in that data, there was a tiny sharp point of light, labelled SWAN, sitting about 1.5 arcseconds from the star. On the sky, that angle is small, but at that distance it corresponds to around 2 astronomical units, roughly 186 million miles, or 300 million kilometers, from Alpha Centauri A. That is right in the kind of orbit where a serious planet could live. So what was this thing? Was it just a fuzzy blob? Or did it look like a real object? The first pass through the numbers said, this matches a Saturn-class gas giant. From the brightness in the mid-infrared, at about 15.5 microns, you can estimate how much energy it's emitting. That gave a temperature of around 225 Kelvin, which is about minus 55 degrees Fahrenheit, or minus 48 degrees Celsius. That is cold from a human point of view. Water is ice there, but it is warmer than Saturn's cloud tops, because this object would be closer to its star than Saturn is to our Sun. The brightness also lined up with a planet about 90 to 150 times the mass of Earth, with a radius around 1.0 to 1.1 times that of Jupiter, so roughly 44,000 miles, around 71,000 kilometers, across. In other words, not a super-Earth, not a mini Neptune, a full-scale gas giant. Now here's the part where things stop being routine, and your brain starts to say, hold on, this might be big. That little point, S1, wasn't hovering right at the edge of what JWST can barely detect. Its measured flux, the amount of infrared light hitting the detector, was about 3.5 millijanskis at that wavelength. When the team compared that to the noise level in the image, they got a significance of roughly 4 to 6 sigma. In plain language, that means the signal stands out clearly from random fluctuations, and the probability that this is just a coincidence in the noise is extremely small. Scientists see junk in data all the time. They're used to throwing away weak hints. This one was strong enough that nobody felt comfortable just calling it a glitch and moving on. So at this point you have a simple story. JWST has found a Saturn mass gas giant, about 2 astronomical units from a Sun-like star, in the nearest star system. Done. Right, not even close. Because after that first detection in August 2024, the logical next step was obvious. Look again. The team scheduled 2 more JWST visits, one in February 2025 and one in April 2025. Same instrument, same chronograph, better planning, deeper exposures, higher sensitivity. They pointed the telescope right back at Alpha Centauri A, checked the location where S1 had been, and also checked the range of nearby positions where a planet on a 2 to 3 year orbit might have moved in a few months, and this time nothing showed up. No S1, no slightly dimmer version, no shifted version. Down to fainter brightness levels than before, the spot where S1 had been was empty. So now the question gets sharper. If the object was real, how can it disappear in less than a year? And if it wasn't real, how did it look so convincing in that first dataset? The obvious first guess is, okay, must be an instrument artifact. That would be the safe answer. A bad pixel, some internal reflection, a weird pattern left over from subtracting the star's light. But this is the nearest Sun-like star, nobody's treating it casually. Teams went through the raw data and the processing steps in detail. S1 didn't line up with known bad pixels. It didn't match the symmetry patterns you expect from optical ghosts. It didn't repeat when they looked at other stars with the same settings. And it appeared as a point source, with the same shape as a real astronomical object blurred by the telescope, not as a stretched smear or a ring. If it's not a normal artifact, what else could it be? One option is a background object, like a distant galaxy or a faint star behind Alpha Centauri, but that runs into another simple problem. Background objects don't care about our observing schedule. They don't vanish in a few months. A galaxy at hundreds of millions of light-years distance would sit in the same spot on the sky in 2024 and in 2025. The fact that S1 is there once, then not there later, already makes that explanation very unlikely. Another option is a clump of dust, maybe a bright knot in a thin cloud in the system, but its compact shape and colour do not fit nicely with that either, and the overall dust in the system seems low. So astronomers are forced into a very uncomfortable shortlist. Option 1, this was an incredibly unlucky statistical fluke, a rare noise spike that by chance looked perfect. Option 2, it was some strange short-lived dust structure that brightened briefly in mid-infrared and then faded below our detection limit. Option 3, it really is a planet, on an orbit that carried it into JWST's worst blind zone for the follow-up observations, somewhere too close to the star or sitting where the coronagraph and the residual glare make it invisible, even if it is still there. None of these options is fully satisfying, but you cannot just pick your favourite, you have to let the data force your hand. Now step back and look at the stakes, because this is where it stops being just a technical problem. If S1 is real, then the nearest Sun-like star probably has a Saturn mass gas giant circling between about 1 and 2 astronomical units, right in its habitable zone. That would make it the closest directly imaged gas giant in a temperate orbit we've ever seen, not hundreds of light years away. 4. That turns Alpha Centauri from a distant target on mission, slides into an actual neighbourhood with a large world in a warm orbit that we can point to and name. It means that when you look out into the night sky and think nearest star, you're not just thinking about light, you are thinking about a specific planetary system, one step away from our own. So here is the tension you're sitting in right now. Did humanity just spot its closest giant planet and then lose sight of it? Or did the most powerful space telescope we have get tricked at the edge of its capabilities? To push that question further, you need to understand what this star system really looks like. How many stars are involved, what else orbits there, and why Alpha Centauri has always been the #1 target for interstellar mission plans. How many stars does your nearest star system actually have, and how many of them are now under suspicion for hiding planets? When you hear Alpha Centauri, you probably picture one star, one target, one place to point a future spaceship. In reality, before S1 even entered the story, Alpha Centauri was already a 3-star system that astronomers have been watching for decades, because it is basically a small, compact test lab for everything we care about in planetary systems. Start with Alpha Centauri A. This is the star that S1 seems to orbit. It's a G-type star, the same general class as our Sun, but about 10% more massive and roughly 50% more luminous. If you swapped our Sun for Alpha Centauri A, Earth would suddenly be getting a lot more energy. Right next to it, gravitationally speaking, is Alpha Centauri B, a slightly smaller and cooler K-type star. It's around 90% of the Sun's mass, and shines at about half the Sun's brightness. These two stars orbit each other on a long, stretched path, taking about 79 years to complete one loop. At their closest, they are about 11 astronomical units apart, similar to Saturn's distance from the Sun, around 1 billion miles, 1.5 billion kilometres. At their farthest, they stretch out to more than 35 astronomical units, beyond the average distance of Pluto. It's a wide stow but very real binary system, not a simple single star plus planet setup like our own backyard. Then there's the third member, which complicates the picture even more. Farther out, on a huge loose orbit around this pair, sits Proxima Centauri, a dim red dwarf star. Proxima is actually the closest individual star to the Sun in pure distance, but it's tiny and faint compared to A and B. Even so, it already has at least 2 confirmed planets. One of them, Proxima b, is roughly Earth mass and sits in the star's habitable zone, where surface liquid water could, in principle, exist if conditions are right. So before anyone talked about S1, this system already had a bright sun-like star, a cooler companion, a red dwarf tag-along, and confirmed planets around the smallest one. You're not looking at some empty, boring corner of space. So why has this one system, out of billions of stars in the galaxy, been treated as the holy grail by mission planners if you're designing real missions, not just sci-fi concepts? Alpha Centauri jumps to the top of the list almost by default. First, distance. At about 4.37 light-years, roughly 25.6 trillion miles, 41.2 trillion kilometers, it is brutally far by today's standards, but it is still the closest sun-like system you can go to. Everything else in that category is farther. Second, the stars themselves are appealing. Alpha Centauri A and B are bright, stable, middle-aged stars, roughly 5 to 6 billion years old, comparable to the Sun. That age matters because it means any planets there have had time for long-term climate and geology, not just a brief chaotic youth. On top of that, we already know Proxima has planets, including Proxima b, an Earth mass world in its habitable zone. That alone made Alpha Centauri a prime target. 1 system, 3 stars, at least 1 potentially temperate rocky planet already on the books. Now, when you add probable Saturn mass gas giant in the habitable zone of Alpha Centauri A to that list, the picture shifts. You're no longer talking about 1 interesting planet. You're talking about a mini ecosystem of potential worlds and moons spread across 3 different stars, all in the closest system available. For anyone thinking about long-term exploration, that looks less like a single destination and more like a starter cluster of targets, all bundled into 1 address in space. But is S1 really the first time Alpha Centauri A has hinted at a planet? Or has it been signalling us for longer and we just didn't take it seriously enough to answer that? You have to rewind to 2019, years before JWST launched. At that time, an experiment called NEAR, operating on the Very Large Telescope in Chile, pointed a custom mid-infrared instrument at Alpha Centauri A. In that data, the team picked up a faint mid-IR source they called Candidate 1, or C1, sitting at about 1.1 astronomical units from the star. That's roughly 102 million miles, 165 million kilometers, a bit closer in than Earth is to the Sun. C1 was interpreted as a possible planet with a mass somewhere between Neptune and about half of Saturn. The data were noisy, the detection was right on the edge of what the instrument could do, and follow-up observations never nailed it down. So it stayed in the literature as Alpha Centauri Ab, a candidate, not a confirmed planet. For a while, many people mentally filed it under interesting but maybe noise. The twist now is that the distance and the brightness of C1, when you run the orbital math forward a few years, line up surprisingly well with where S1 shows up in 2024, if you assume a 2 to 3 year, somewhat stretched orbit. It is not proof, but it's a pattern. 2 different telescopes, years apart, both see something in the mid-infrared at distances that a single eccentric orbit could connect. If that connection is real, what kind of system are you actually looking at? You now have a bright, sun-like primary star, slightly more luminous than our Sun. You have a binary partner star that swings in and out, sometimes coming close enough to tug on any planets and debris around A. You have a distant red dwarf with its own planets, including a temperate Earth mass world. And layered on top of all that, you likely have a Saturn mass gas giant in the region where liquid water could exist on moons or smaller companion planets. Put simply, this setup is not quiet. It's a dynamically rich neighborhood where gravity is constantly shaping orbits, disks, and potential worlds. Because it is so close, people have not just daydreamed about going there, they have drawn up actual engineering concepts. Things like laser-driven light sails, wafer-scale probes accelerated to significant fractions of the speed of light, all aimed at Alpha Centauri as the first realistic interstellar destination. At 4.37 light-years, even with very optimistic technology, you're still talking about the travel times measured in decades, not years. But if you know there are multiple stars, known rocky planets, and now a likely gas giant with possible moons, motivation to turn those concepts into real missions jumps dramatically. The system looks less like a single target and more like a small, reachable cluster for humanity's first serious push beyond the solar system. So how empty is the space between us and that system really? And how close does a nearest star feel when you scale it to something more familiar? Here's one way to frame it in your head. Take the distance from Earth to the Sun, about 93 million miles, 150 million kilometers, and shrink it down until it's just 1 yard, around 0.9 meters. On that scale, the entire orbit of Earth is a circle about 2 yards across. Now, where is Alpha Centauri A on that same scale? At 4.37 light-years, it ends up roughly 276 miles, 444 kilometers away. That's like putting the Sun in New York City, shrinking Earth's orbit to the size of a tiny circle around it, and then placing Alpha Centauri A down near Richmond, Virginia. Nothing but mostly empty space in between, and yet in that huge gap, S1 would still be the closest likely gas giant outside our solar system that we have ever imaged. So now you know the stage: 3 stars, known planets, a possible gas giant, and a lot of gravitational drama packed into the nearest system. But how did JWST even manage to pull off that first shot of S1 in such a harsh environment, and what kind of technology does it take to see a faint planet next to a bright star at that distance? Why does a telescope have to live 1 million miles from Earth just to catch one faint dot next to Alpha Centauri? The trick with JWST starts before any light even hits its mirror. The observatory sits at the Sun-Earth L2 point, about 1 million miles, 1.5 million kilometers, from Earth on the night side of our orbit. There, a huge multi-layer sunshield keeps the entire telescope chilled to just a few dozen degrees above absolute zero. That extreme cold matters because JWST looks in infrared, the kind of light that warm objects naturally glow in. If the telescope itself were warm, it would drown its own detectors in thermal noise. On top of that, the primary mirror is big, 21.3 feet, 6.5 meters across, made of 18 gold-plated beryllium segments, with a collecting area of about 270 square feet, 25 square meters, roughly 6 times Hubble's. A mirror that large grabs more photons, and the cold optics keep the background low, so when a planet is 10,000 to 100,000 times fainter than its star in the mid-infrared, the telescope still has a shot at pulling that planet's glow out of the star's glare. So how do you actually switch off a star that bright without also killing the planet's signal you want? That is where JWST's mid-infrared instrument, MIRI, and a coronagraph come in. For the Alpha Centauri observations, astronomers used a special mask built into MIRI that blocks the core of the star's light on the detector. You can think of it very literally as hiding the blinding central spot so you can look at the region around it. Once the star's peak is suppressed, MIRI records the mid-infrared light at wavelengths like 15.5 microns, where a planet with a temperature of about 225 Kelvin, around minus 55 degrees Fahrenheit, minus 48 degrees Celsius, gives off a steady thermal glow. The surrounding dust, if it is colder, emits less strongly there, so the planet stands out more. In August 2024, after a carefully tuned observing sequence and a lot of calibration work, that setup produced a clean point source at about 1.5 arcseconds from Alpha Centauri A, with a brightness of roughly 3.5 millijansky's at that wavelength. That compact, repeatable dot in the processed image is what the team labelled S1. But how extreme is the contrast problem JWST is actually fighting here? The numbers are rough, but they are brutal. Alpha Centauri A is about 1.5 times as luminous as the Sun, so it is already a very bright mid-infrared source at that distance. A Saturn-mass planet at around 2 astronomical units, glowing at about 225 Kelvin, is something like tens of thousands, up to 100,000 times fainter than the star in the mid-infrared band MIRI is using. On the detector, the planet's light sits only about 1.5 arcseconds away from the core of the star's point spread function, the pattern of light the telescope optics produce. The MIRI coronagraph has to knock the starlight down, leave behind only a structured pattern of residual speckles, and then the data pipeline subtracts a reference pattern, built from either models or other observations, to remove as much of that leftover pattern as possible. What you hope remains, after all of that subtraction, are real astrophysical sources, not false speckles. JWST's system is pushing down to contrast levels of a few times 10 to the -5 at those separations. That is why the team is so cautious, because at that level, you're operating right at the edge of what the hardware and software can do. If the hardware is that good, why are scientists still nervous about calling S1 a confirmed planet? The key weakness in the initial observation is not the mirror, or the instrument. It is the geometry of the observation itself. In August 2024, the successful dataset for Alpha Centauri A only reached one useful roll angle. Rolling the telescope means rotating it so that the sky, and any real planets, move relative to the internal speckle pattern of the optics. With multiple roll angles, a true planet shows up moving in a consistent circle around the star, while static speckles stay locked to the detector pattern. With only one working orientation, you don't have that strong test. S1 shows up as a point source in that single roll, but you cannot watch it shift relative to the internal noise pattern. That makes it harder to rule out a clever combination of residual speckles and subtraction artifacts that just happen to stack into something planet-like. So what does that leave you with? In terms of next steps, JWST has demonstrated that it can, in principle, see objects as faint and as close in as S1 appears to be. It has already passed the hardest engineering barrier, doing high-contrast imaging in the mid-infrared around the nearest Sun-like star. The remaining problem is not the telescope's raw power, it is time and orbital phase. The planet, if it is real, is moving. To prove that S1 is not a fluke, you have to come back in future years, point MIRI and the coronagraph again, and see whether a similar point of light appears at the positions that orbital calculations predict. That is why there is so much focus on observation windows in 2026 and 2027, because those are the likely times when S1 on a 2 to 3 year orbit would swing back into regions of the coronagraph's field where JWST is most sensitive. And this is where the story stops being only about JWST and turns into a preview of every future planet-hunting telescope we want to build if one observatory with a 21-foot, 6.5-meter mirror and a first-generation coronagraph can even hint at a Saturn-class planet at around 2 astronomical units from a bright G-type star 4.37 light-years away. Then the next wave of missions can go further. The Nancy Grace Roman Space Telescope will fly with an even more advanced coronagraph in visible and near-infrared light, with tighter stability and better wavefront control. Beyond that, proposed LUVOIR or HABEX-class observatories, with much larger mirrors, are designed specifically to image Earth-sized planets in habitable zones around Sun-like stars. In that context, S1 is basically the dress rehearsal, the hard practice run where we learn how to deal with contrast, speckles and orbits, right in the nearest system. So if JWST has already shown us that this kind of planet is barely visible but not impossible to catch, the obvious next question is simple. What do we actually know about S1 itself, its orbit, its temperature, its mass, and how much of that picture is solid versus guesswork balanced on one risky detection? How much can you really say about a planet when you've only seen it once in one wavelength for a few hours, it turns out? A lot more than you'd think, and at the same time way less than you'd like. With S1, the starting point is simple geometry. On the sky, it sits about 1.5 arcseconds away from Alpha Centauri A in that August 2024 JWST data. At a distance of 4.37 light-years, that angle translates to roughly 2 astronomical units, about 186 million miles, around 300 million kilometers from the star. That's the raw projected separation, the shadow of its orbit on the sky. When you combine that snapshot with the older C1 detection from 2019 and you ask, what kind of orbit could hit both these positions at the right times, you start to get a family of possible paths. Those orbital models point to a period of roughly 2 to 3 years. That means S1 would take about 2 to 3 Earth years to make one full loop around Alpha Centauri A. The orbit doesn't look like a nice, perfect circle either. The best fits give an eccentricity around 0.4, which is noticeably stretched out. In solar system terms, that means S1 is likely swinging between roughly 1 and 2 astronomical units, from about Earth-Mars distance on the inside to just beyond Mars's orbit on the outside if you imagine it around our Sun. Now plug the star into that picture. Alpha Centauri A. A is roughly 1.5 times as luminous as our Sun, so its comfort zone for liquid water sits farther out. For a star like that, the habitable zone, the region where a solid planet with an atmosphere could keep liquid water on its surface, spans roughly 1 to 2 astronomical units. That's exactly where S1's orbit seems to live. So when people say gas giant in the habitable zone, that's what they mean here. Not that S1 itself is habitable, but that it's cruising through the distance range where an Earth-like world or a moon would get roughly the right amount of stellar energy. So what about S1's actual bulk? How big is this thing and how heavy? You take the brightness from JWST and the earlier mid-infrared imaging, you factor in the estimated temperature of about 225 Kelvin, and you get radius and mass estimates. The models that match the brightness say S1's radius is around 1.0 to 1.1 times Jupiter's radius, roughly 44,000 miles, about 71,000 kilometers across. That's huge compared to Earth. And the mass comes out around 90 to 150 Earth masses, squarely in Saturn-class territory. This is not a super-Earth, this is a gas giant. At about 225 Kelvin, minus 55 degrees Fahrenheit, minus 48 degrees Celsius, S1 is colder than Earth, but warmer than Jupiter's cloud tops. That makes sense. It's sitting closer to a slightly brighter star. From the standpoint of planet physics, that temperature range plus that size and mass is exactly where you expect a Saturn-like gas giant to land, with thick clouds, deep atmosphere, and a lot of internal structure. At that mass, the composition picture is pretty straightforward, and this is where some people's mental image of maybe it's a big rock needs to be corrected. A planet 90 to 150 times the mass of Earth is not a scaled-up rocky world. It lives firmly in gas giant territory. The outer layers are almost all hydrogen and helium. Underneath that, you expect a heavy element core, maybe 10 to 20 Earth masses worth of rock and ice, similar to Saturn, buried deep below thousands of miles of high-pressure fluid. As you go deeper, the hydrogen doesn't stay a normal gas. It transitions into exotic states, including metallic hydrogen, where it conducts electricity and feeds a strong magnetic field. So if you're picturing your future interstellar mission landing somewhere, S1 is not the surface you're landing on. There is no solid ground to stand on, only layers of cloud, wind, and crushing pressure. The realistic scenario is that you're orbiting S1, not touching down. You're interested in what could be around it. Large moons, maybe Trojan companion objects sharing its orbit. The gas giant itself is a gravitational anchor, a heat source for nearby moons, and a giant lab for atmospheric physics, not a place to walk. Now, the orbit gets even weirder when you look at how S1 seems to be tilted relative to the rest of the system. To keep the planets stable in the combined gravity of Alpha Centauri A and B, dynamical models suggest that S1's orbit is not nicely lined up with the AB binary plane. Instead, its mutual inclination likely sits around 50 degrees or possibly around 130 degrees relative to that plane. In plain language, the orbit is significantly tilted. It's not quietly lying in the same flat sheet as the main binary orbit. That tilt is not just a detail, it's a clue. It hints that something in the past kicked this planet's orbit out of alignment. Maybe the protoplanetary disk around Alpha Centauri A got warped by the gravity of Alpha Centauri B. Maybe S1 migrated inward or outward and had close encounters with other giant planets that were later ejected or swallowed. Maybe long-term gravitational interactions over hundreds of millions of years slowly pumped up its inclination. Whatever the exact story, a tilted, eccentric orbit in a binary system usually means a dynamic history, not a calm, undisturbed formation. Then there's the environment S1 is moving through. JWST's observations of exozodiacal dust around Alpha Centauri A have set the tightest limits we've ever measured around a sun-like star. The data say the dust in the inner system is no more than about 5 to 8 times the brightness of our own zodiacal cloud, the thin dust that causes zodiacal light in our solar system. For direct imaging, that's a big deal. Dust scatters light and glows in infrared, making it harder to see planets. Low dust means a cleaner background. For the system itself, it means SER-1 is living in a relatively clean low-dust environment, not ploughing through a thick debris field. From a planet formation and habitability perspective, that's exactly what you'd want if you're trying to support long-lived moons or inner rocky planets. Less dust usually means fewer recent giant collisions between big bodies. If huge Earth-sized worlds were smashing into each other in the habitable zone, JWST would likely see hotter, brighter dust plumes. The absence of those plumes suggests a system that has calmed down enough for planets and moons to keep stable orbits over long time scales. S1, if real, is not just sitting in the right distance range, it's in a relatively clean zone where smaller worlds could quietly orbit and evolve. But now we hit the brakes, because all of this, as compelling as it sounds, sits on top of that one big word you keep hearing, candidate. There's a reason astronomers repeat it. On the one hand, the radial velocity data we have for Alpha Centauri A, the method where you watch the star's spectrum wobble as planets tug on it, can already rule out planets more massive than about 150 Earth masses at these distances. S1's estimated mass, 90 to 150 Earths, lives right under that current detection ceiling. That means RV data can't yet kill the planet hypothesis, but it also can't confirm it. The signal it would produce is just too small and too tangled up in the binary dynamics for current instruments to see clearly. On the other hand, the 2025 JWST non-detections don't automatically prove S1 was fake. When you run orbital models that link C1 in 2019 and S1 in 2024, and then ask, where would this planet be in early 2025? A lot of the allowed orbits put it right in the worst parts of the coronagraph's field, the inner working angles and high noise zones where JWST is least sensitive. Simulations suggest there's about a 52% chance that if S1 is real and on one of those orbits, it would have been hidden from view in both 2025 observations. That is not a guarantee, but it's enough that we didn't see it in 2025 does not kill the planet either. So you're walking a tight line here. On one side you have a coherent picture, a Saturn-class gas giant at 1 to 2 astronomical units, tilted and eccentric in a clean habitable zone, connecting hints from 2 different telescopes. On the other side you have the brutal reality that this rests on a single strong detection and a lot of modelling, with follow-up data that are ambiguous rather than confirming. The stakes are huge, because if S1 is real, it becomes the closest gas giant in a habitable zone we've ever seen, and it completely reshapes how we think about the nearest star system. If it's not real, it becomes a warning about how easy it is to fool ourselves at the edge of instrumental sensitivity. And that sets up the next hard question you have to tackle. If S1 really is a planet with all these specific properties, why did it show up once and then vanish? Are we watching orbital mechanics play a trick on us? Or did JWST catch something else entirely in that first shot? How do you trust a signal that showed up once, clean and sharp, and then refused to come back? This is the core problem with S1. In August 2024, JWST gives you one dataset, one usable roll angle, and in that frame you get a clear 4 to 6 sigma point source at about 1.5 arc seconds from Alpha Centauri A. Not a smear, not a messy blob, a compact dot with the right brightness and colour to match a Saturn-class gas giant. That's the detected once part. Then in February 2025, and again in April 2025, you point the same telescope with the same instrument at the same star. You go deeper, you push to stricter brightness limits, and you find nothing at that position, and nothing obvious nearby that would be the same object shifted along an orbit. That's the missed twice part. If S1 were just a random background galaxy sitting far behind Alpha Centauri, it would not care about our schedule. It would be in the same place in 2025 that it was in 2024 within tiny fractions of an arcsecond. The fact that it's there in one epoch and gone in the next two basically kills the simple background object explanation. If it was simple instrumental noise, a glitch in the detector, you'd expect it to look messier. You'd see shapes that don't match the telescope's point spread function, or patterns that line up with known bad pixels, or artifacts that recur in other data sets with the same setup. Instead, S1 shows up as a clean point, at exactly the kind of separation where a real planet could live. That combination, strong once, gone later, is why people are taking this so seriously and at the same time refusing to just declare victory. So if it's not a background object and not obviously garbage, what's the leading idea? The main working explanation right now is not exotic. It's straight orbital mechanics combined with instrument limits. If S1 is a real planet on a 2 to 3 year orbit, then over the 6 to 9 months between August 2024 and the early 2025 follow-ups, it doesn't just sit there. It moves by tens of degrees along its path around Alpha Centauri A. On the sky, that motion changes both its separation from the star and its angle. In some parts of that orbit, as seen from JWST's vantage point, the planet's projected position can slide into regions close to the star where the chronograph just doesn't perform well. Those regions have names in the technical docs: inner working angles, diffraction spikes, zones dominated by residual speckle noise. In plain language, those are spots where the star's leftover glare is still strong enough that even a real planet of S1's brightness would be buried. Simulations that connect the 2019 C1 detection and the 2024 SO1 point, and then evolve the orbit forward, show something interesting. If C1 and S1 are the same object, on one of the allowed orbits, there's roughly a 52% probability that the planet would have been hidden in those bad sensitivity zones during both 2025 observing windows. That number matters because it says no detection in 2025 is not a surprise if the planet is real. It's not proof, but it's consistent. That still leaves you with an obvious challenge though. Could SWAN just be some kind of dust structure or processing artifact that happens to look planet-like? This is where the details of the data push against those ideas. If S1 were a clump of exozodiacal dust, you would expect some extended structure, a slightly smeared out feature, or a clear link to a larger disk pattern. Instead, S1 looks like a point source. Its shape on the detector matches what you get from a compact object blurred by the telescope, not a spread out cloud. Its brightness and colour also don't match what you'd expect from a dust clump in a disk that's already constrained to be less than about 5 to 8 times our solar system's zodiacal dust brightness. In other words, there just isn't that much warm dust to work with. What about pure instrumentation tricks, things created by the optics or the data processing pipeline? The usual suspects: there are speckles that repeat in specific locations relative to the star, artifacts that track with the roll angle, or patterns that show up across many observations with similar setups. S1 doesn't behave like that. It doesn't map onto known stable speckle structures, it doesn't repeat in other targets, and it shows up only in that specific 2024 configuration. None of this absolutely proves planet, but it steadily removes the simpler non-planet explanations. You end up with a situation where the planet hypothesis is not guaranteed, but it is the one that best fits all the current constraints without forcing too many special exceptions. This is exactly why some astronomers have used very strong language about S1, but with heavy caveats. You'll see quotes calling it potentially the most significant JWST finding to date. If it holds up, and that's not exaggeration. If confirmed, S1 would be the closest directly imaged exoplanet ever found, and the closest known planet in the habitable zone of a Sun-like star. Not just an interesting point in a catalogue, but a cornerstone object for exoplanet science, sitting 4.37 light-years away. That's why it hits so hard. It's not another gas giant 100 light-years out. It's in the system people have been dreaming about visiting for decades. But listen carefully to the way those same scientists talk in the next sentence. They always add that this signal sits at the edge of JWST's contrast capability, right where the subtraction of starlight is hardest and the risk of self-deception is highest. They emphasize that independent confirmation, ideally by different methods or instruments, is mandatory before anyone should call S1 a confirmed planet. The last thing the field wants is to declare the nearest gas giant in the habitable zone and then have to retract it because of some subtle processing mistake. So the tone is a mix of excitement and strict caution, and both are justified. So what happens next? Do we just sit with maybe forever? Not really. The orbital fits that tie together C1 and S1 don't just explain the past, they predict the future. If those orbits are close to right, S1 should move out of JWST's blind spots and swing back into regions of the coronagraph field where the telescope is sensitive again sometime in 2026 or 2027. That's the key window everyone is watching. Targeted JWST campaigns in that timeframe can point mirror-eye back at Alpha Centauri A, dial in the expected positions and look for a point source with similar brightness and colour to the 2024 detection. If a new dot appears roughly where Kepler's laws say it should, with the same mid-infrared characteristics, the disappearing planet story flips. It stops being a cautionary tale about pushing an instrument too hard and turns into a clean confirmation arc. First hint with NEAR in 2019, sharper detection with JWST in 2024, orbital reappearance in 2026 to 2027. At that point, S1 goes from candidate to confirmed very fast, and everything from planet formation models to interstellar mission concepts has to absorb that reality. If nothing shows up, on the other hand, even in the best parts of the field, then the balance tips the other way, and the community will have to seriously consider that the 2024 signal was a rare, very convincing false positive. Either way, those re-observation windows are not just technical details, they are the turning point of the story you're in the middle of. And to really see how we got here, and why so many people are willing to even consider that this one object might be real, you have to rewind to the first time Alpha Centauri A flashed a suspicious mid-infrared signal at us, years before JWST ever took its shot. How far back does this story really go, and did we already see this planet once, shrug and move on, long before JWST ever looked at Alpha Centauri A? You have to rewind to 2019. Back in May and June of that year, the VLT/NEAR experiment in Chile pointed a custom mid-infrared camera at Alpha Centauri A and just stared. NEAR was built for one job, to push the very large telescope to its limits in the mid-IR and see if anything warm and faint was sitting near that star. When the team went through the data, they pulled out a very faint signal at about 1.1 astronomical units from Alpha Centauri A, roughly 102 million miles, about 165 million kilometers away from the star. They called it Candidate 1 or C1. C1 was not a clean textbook detection. The data were noisy, the signal sat near the sensitivity floor, and there were a lot of ways things could go wrong. But when they modelled its brightness, they got something in the range of a Neptune to sub-Saturn mass planet. Not an Earth, not a tiny rock, but something likely in the gas or ice giant family. Because the evidence wasn't strong enough to claim a discovery, they did the cautious thing. They catalogued it as Alpha Centauri Ab, a candidate planet, and made it very clear it was not a confirmed world. For most people, even in the field, C1 was cool if true, but probably noise, and attention moved on. Now jump forward to 2024, JWST looks at Alpha Centauri A and finds S1 at around 2 astronomical units. That's almost twice as far out as C1's 1.1 astronomical unit. The obvious question is, are these two independent hints, two different possible planets, or are they actually the same object seen at two different points along one orbit? When you assume a single planet and try to connect the dots, the numbers start to line up in a very suggestive way. If C1 was the planet near its closest approach to the star, periapsis, at about 1.1 astronomical units in 2019, and S1 is the same planet near its farthest point, apoapsis, at about 2 astronomical units in 2024, you can fit a single eccentric orbit through both positions. The best fits give you an orbital period of roughly 2 to 3 years, an eccentricity around 0.4 and a path that swings the planet back and forth between those distances. When teams combine the VLT/NEAR data, the JWST data, and the later non-detections, they do not get one perfect orbit, they get families of orbits. But a lot of those families are fully consistent with C1 and S1 are the same thing, and we just caught it twice at different points and missed it when it was in bad regions of the coronagraph. If that's what's really going on, then Alpha Centauri Ab, this candidate from 2019, gets promoted from a maybe noise blip to something much more serious. In that case, Ab/S1 is not just another planet, it becomes the system architect for Alpha Centauri A. Here's why that matters. A Saturn-class gas giant at 1 to 2 astronomical units has a deep gravitational reach. It controls a hill sphere tens of millions of miles wide, where large moons can orbit stably for billions of years. It shapes where smaller rocky planets can exist closer in by either protecting them from, or driving them into, collisions with debris. Its eccentric orbit can clear out belts of smaller objects, rearrange dust, and carve structures into any leftover disk. When JWST now tells you that the exozodiacal dust around Alpha Centauri A is very low, no more than about 5 to 8 times our own zodiacal cloud brightness, that might not be a coincidence. A big gas giant on a stretched inclined orbit could have spent its early life scattering planetesimals, vacuuming up debris and thinning out the inner system. The dust pattern you see, or don't see, today might be the direct result of Ab/S1's long-term gravitational work. That's what people mean when they call it a system architect. It sets the layout of the whole neighbourhood. So why is direct imaging such a big deal in this story? Why not just use the classic planet hunting tools we've used for thousands of other exoplanets? The problem is that Alpha Centauri A is a tough target for those traditional methods. Radial velocity, where you watch the star's spectrum shift as it wobbles, struggles because the star is very bright, very close, and part of a tight binary with Alpha Centauri B. The gravitational pull from B sits on top of and can hide the much smaller signals from a Saturn-mass planet at 1 to 2 astronomical units. On top of that, the star's own activity and noise make it hard to pull out a low-amplitude signal at the level S1 would produce. Transits are not much better. For Swan to transit, it would have to cross directly in front of the star from our perspective. With a tilted non-edge-on orbit and a relatively large distance from the star, the geometric chance of that happening is low. Even if it did transit, the dip in light would be shallow and rare, and you'd need long, continuous monitoring locked onto Alpha Centauri A, which we haven't had at that precision. That's why radial velocity and transits have not already nailed down a planet like this, even in the nearest system. Direct imaging, especially in the mid-infrared, jumps over those problems. You're not waiting for the star to wobble or dim, you are literally catching the planet's own light. In this case, you're seeing its thermal glow at around 225 Kelvin. That single snapshot gives you position, approximate temperature, and, when you combine it with models and other data, reasonable estimates for radius and mass. For Alpha Centauri A, that's the one channel that can cut through the mess of the binary system and the lack of transits. It's also why these mid-IR detections are such a big deal, even if they're right at the edge of what's possible. Back in 2021, when people looked at C1 and Alpha Centauri AB, the mindset was very different. It was interesting, yes, because it was around the nearest Sun-like star, but the detection was so marginal that it was easy to mentally file it as probably noise and move on to clearer, more distant systems. There was no second, independent telescope seeing the same thing. There was no JWST follow-up. If you weren't already obsessed with Alpha Centauri, C1 was background noise in the flood of exoplanet news. In 2025, that attitude doesn't work anymore. With S1 on the table, the narrative has flipped. Now you have two independent instruments on two different telescopes, using similar wavelengths, both pulling out mid-infrared signals at distances that a single eccentric orbit can connect. You have a plausible shared period and eccentricity, and orbital models that explain not only where the planet might be, but also why it might have been invisible in 2025. And all of this is happening not around some star 200 light-years away, but in the nearest Sun-like system. That combination is why you're now watching astronomers talk about dedicated follow-up missions for Alpha Centauri with a straight face. Concepts that were once just slides in conference talks, like specialized space telescopes aimed only at the Centauri system, or more advanced interferometers to pick apart its planets and dust, are now being discussed as serious proposals. If Ab S1 is real, the argument becomes simple. We know there's a big gas giant in the habitable zone of the closest Sun-like star. We need hardware built specifically to study that system. And that pushes you into the next question. If there really is a Saturn-class planet sitting in the habitable zone 4 light-years away, what does that actually mean for habitability, for moons, and for the idea of a Pandora-style world in this system? How can a planet sit right in the just right zone for liquid water and still be totally off limits to anything that needs solid ground? That's the first mental reset you have to make with S1. When astronomers say habitable zone around Alpha Centauri A, they mean roughly 1 to 2 astronomical units from the star, about 93 to 186 million miles, 150 to 300 million kilometers. In that band, an Earth-like planet with an atmosphere could keep liquid water on its surface. Because Alpha Centauri A is about 1.5 times as luminous as the Sun, that comfort zone gets pushed a bit farther out than our own. S1's orbit, from roughly 1 to 2 astronomical units, sits right in that band. But S1 itself is a gas giant, with no solid surface, just deep layers of gas and fluid. You're not building cities there, you're not landing there at all. Habitable zone here does not mean nice place to live, it just means the sunlight level is about right for liquid water somewhere, if you have the right kind of world. So if the main planet is basically a giant ball of hydrogen and helium, where does that leave any serious talk about habitability? This is where the focus shifts from the planet to what could be orbiting it. Gas giants in habitable zones turn into moon laboratories. A Saturn-class planet at 1 to 2 astronomical units around a Sun-like star has a gravitational region, the Hill sphere, that stretches out hundreds of thousands to millions of miles from the planet, where moons can orbit stably for billions of years. In our solar system, moons like Ganymede and Titan already show you how big and complex satellites can get. Around S1, the physics allow for even larger ones. If S1 exists with the mass we think it has, it could host moons that are Mars-size or bigger, with radii around 2,100 miles, 3,400 kilometers, or more, bodies that large can hold dense atmospheres for billions of years, keep liquid water under the right conditions, and run real geology. There is zero direct evidence yet for such moons around S1. Our current instruments can barely see the planet, let alone anything orbiting it, but nothing in orbital mechanics or planet formation says they can't exist. Combine that with the low dust environment and the likely long-term stability of the system, and suddenly the most interesting, habitable real estate in Alpha Centauri A's habitable zone might not be planets at all, but big satellites circling this gas giant. Even if those moons exist, is starlight alone enough to keep them active and interesting over billions of years? Not necessarily. And that's where the double power source idea comes in. Any moon orbiting close enough to S1 would feel its gravity flexing the interior over and over as it moves along its orbit. That flexing tidal heating is the same process that makes Jupiter's Io so volcanically active and Saturn's Enceladus warm enough to keep subsurface oceans and geysers going, even far from the Sun, and move that setup into a much brighter environment. Put a large moon around S1 at 1 to 2 astronomical units. It gets a sunlight level not too far from what Earth gets, thanks to Alpha Centauri A. On top of that, it gets internal heat from tides raised by the gas giant. Those two energy sources together, stellar flux plus tidal heating, give you a big flexible energy budget for climate and geology. You can power thick atmospheres, long-lived oceans, active plate tectonics, and deep subsurface layers all at once, in principle. That's why you see cautious references to a real-life Pandora in some discussions, not because anyone has seen such a moon, but because the combination of a gas giant in a habitable zone and possible large moons is exactly the kind of setup that could, on paper, support complex environments. Scientists are very careful to label this as speculation though. Right now it's a could be, not a we see it. But if this kind of gas giant plus moon scenario is so interesting, why is S1's location such a curveball for the way we think planets form? Traditional models say that gas giants tend to form beyond the snowline. That's the region in the young disk where temperatures are low enough for water and other volatiles to freeze into ice, usually a few astronomical units out, often around 3 to 5 AU for sun-like stars. Ice solids out there give you more raw material per unit area, so giant cores can form faster and pull in huge hydrogen-helium envelopes before the gas disk disappears. Seeing a Saturn-class planet apparently parked at 1 to 2 astronomical units in a tight binary system forces awkward questions. Did S1 form farther out beyond the snowline, and then migrate inward through the disk, driven by interactions with gas and other planetesimals, ending up in the habitable zone later? Or did the presence of Alpha Centauri B, swinging between about 11 and 35 astronomical units, warp and reshape the protoplanetary disk so much that the effective snowline moved inward, letting giant cores form closer in than usual? The fact that S1's best fit orbit is both eccentric and inclined points toward a dynamic, messy past. Those orbital properties often show up when planets have scattered off each other or have been torqued by a companion star over long timescales. In other words, if S1 is real, it probably did not have a quiet childhood. If the past was that chaotic, why does the system around Alpha Centauri A look so clean today? That's where the dust measurements become crucial. JWST has set an unprecedented limit on exozodiacal dust in this system. The inner dust around Alpha Centauri A appears to be only a few times brighter than our own zodiacal cloud, not orders of magnitude higher. That tells you there is no massive warm debris disk cluttering the habitable zone. You're not looking at a system filled with constant large-scale collisions of big objects. For small rocky planets and large moons, that low-dust environment is exactly what you'd want for long-term survival. In a system packed with debris, big impacts are common and they can strip atmospheres, melt crusts, and reset conditions over and over. In a system where the dust has thinned out, where giant collisions are rare, solid worlds get time to cool, stabilize, and run long-term climate and geological cycles without constantly getting reset by catastrophic impacts. If S1 is the main architect that helped clear out a lot of that debris early on, then what JWST sees now, a clean habitable zone with a gas giant in it, is the endpoint of billions of years of gravitational cleanup. So you're left with a pretty sharp tension. Sitting only 4 light-years away, there might be a Saturn-class gas giant right in the habitable zone, with room around it for big moons that could, in principle, be very interesting places. The system looks dynamically mature, the dust levels are low, the star is stable, and the orbital story is messy but survivable. At the same time, we've not seen a single moon, we have not confirmed the planet, and we are still pushing JWST to its limits to even test this picture. That naturally raises the next question. If the dust and the planet together make this habitable zone so clean and so promising, how does Alpha Centauri A compare to other systems we've looked at? And is this really the best, cleanest test case we have for imaging temperate worlds beyond the Sun? Why does a little bit of dust between a star and a planet matter as much as the planet itself? If you care about actually seeing these worlds, the dust is your enemy. In our own solar system, there's something called zodiacal light, a faint glow you can sometimes see as a hazy band along the ecliptic just before dawn or after sunset. That glow is sunlight bouncing off tiny dust grains spread across tens of millions of miles in the inner system. It looks pretty, but for high contrast imaging it behaves like fog in front of headlights. It scatters light, it adds background glow, and it makes it harder to see faint planets sitting next to bright stars. Now apply that idea to Alpha Centauri A. When JWST's MirEye instrument stared at this system, one of the goals was not just spot a planet, but also measure how much warm dust is there. The result was sharp. This is no strong zodiacal signature. The mid-infrared data constrain the dust level around Alpha Centauri A to only a few times the brightness of our own zodiacal cloud. That's not no dust at all, but it is extremely clean compared to most systems we've checked. And JWST's sensitivity here is more than 10 times better than what previous instruments could do for similar stars. So you're getting the clearest, deepest look yet at the inner dust environment of the nearest Sun-like star, and it's surprisingly empty. Why should you care about that emptiness if your goal is to send some future telescope to image Earth-like planets? Because dust sets the background noise floor. Picture a future Levoir-class telescope in space with a mirror 26 to 52 feet across, 8 to 16 meters, designed to take actual photographs of rocky planets in visible light. That mission lives or dies on contrast. If the region around Alpha Centauri A were packed with warm dust, all that scattered light would raise the background so much that any faint planet would be buried. No matter how good your mirror is, you cannot beat the physics of a glowing fog in front of your targets. The new JWST limits basically say, this system is not a glowing fog, it's relatively clear. That instantly moves Alpha Centauri A into the top tier of targets for future direct imaging missions. It's close enough that planets in the habitable zone would appear separated by tens of milliarc seconds on the sky. Big enough angles for a large space telescope to resolve with the right coronagraph. And it's clean enough that exozodiacal dust is not obviously a showstopper. If you are building a billion-dollar observatory to go after Earth-like planets, you want nearby, bright, stable and low dust. Alpha Centauri. A just checked all those boxes at once. The lack of dust doesn't just help future cameras, it also tells you something important about the system's past. Dust is produced when things smash into each other, big collisions between Earth-sized planets, or large embryos generate huge amounts of debris, which then grinds down into smaller grains that glow in the infrared. JWST is sensitive enough in the mid-IR that if Alpha Centauri A had recently gone through a catastrophic planet-scale smash-up in its habitable zone, you would expect to see a strong, warm dust signature. Instead, you see only a modest, low-level dust signal. That suggests there haven't been recent giant collisions between big rocky bodies in the 1 to 2 astronomical unit region. In other words, the system doesn't look like it's in the middle of a destructive late-stage chaos phase. For any smaller planets or large moons that might exist around S1, that's good news. It means they have probably had a long stretch of relative stability, with no planet-shattering impacts resetting everything. They've had time to cool, to form solid crusts, to keep or rebuild atmospheres, and to develop complex internal and surface environments if the ingredients were there. It's not proof of anything alive, but it is the kind of background you'd want if you're hoping for long-term steady conditions. So how special is Alpha Centauri A in this respect? Is it just one more point on a plot, or does it actually stand out? Most of the stars where we've managed to set exozodiacal dust limits are much farther away, typically dozens of light years out. For many of them, the dust levels come in significantly higher than our own solar system. Those systems are still interesting, but they are messy. They often have thick belts of debris, more like scaled-up asteroid or Kuiper belts warmed from within. From the standpoint of imaging faint Earth-sized planets, those higher dust levels are a serious handicap. Alpha Centauri A is currently unique in one key way. It's the nearest Sun-like star where we've pushed exozodi sensitivity this low, thanks to JWST's mid-infrared performance and the focus we've put on this system. It's not just that it's close, it's that we've now measured it with tools powerful enough to say, with confidence, this inner region is relatively clean. In a very real sense, Alpha Centauri A is now our best calibrated analogue for what the solar system might look like if some alien civilization pointed their own version of JWST at our sun from a few light years away. They'd see a moderate zodiacal dust level, no giant hot debris cloud in the habitable zone, and maybe, if they were lucky, the glow of our own gas giants and rocky planets. For us, flipping that perspective around is important. It means when we plan missions, simulate observations, or test algorithms for finding Earth-like planets in visible light, Alpha Centauri A can serve as the real-world benchmark instead of a hypothetical system baked into code. We can plug its actual dust level, actual star properties, and candidate planet architecture into our models and ask, would this mission see an Earth analogue here, and what would it look like in real data? That kind of anchored, nearby test case is rare. But even with a clean habitable zone, a nearby star, and a possible gas giant shaping the region, you still have a brutal technical problem sitting in front of you. You're trying to pick out tiny, faint planets right next to a star that is tens of thousands to hundreds of thousands of times brighter, and you're doing it across 4.5 light years of empty space. So the next question is simple and uncomfortable. How is it even possible that we've managed to directly image a candidate planet this close to us at all? And what kind of insane contrast and precision does that actually require? How do you actually see something that is tens of thousands of times fainter than a star, sitting almost on top of it from our point of view? This is where, on paper, directly imaging SWAN should basically be impossible. You've probably heard the firefly and lighthouse analogy before, but here the numbers are even worse than that. Alpha Centauri A is about 1.5 times as luminous as the Sun. S1, if it's real, is a Saturn-class gas giant glowing in the mid-infrared at about 225 Kelvin, roughly minus 55 degrees Fahrenheit, minus 48 degrees Celsius, orbiting somewhere between 1 and 2 astronomical units out. In those wavelengths, the star completely dominates the scene. The planet is tens of thousands to hundreds of thousands of times fainter than the star in the band MIRI is using. MIRI's coronagraph has to slam the star's light down by orders of magnitude, and then the data pipeline has to subtract the star's leftover pattern with ridiculous precision, just to leave a tiny bit of room for that faint planetary glow to peek through. The contrast levels JWST is pushing around Alpha Centauri A are the kind of numbers people used to talk about for future flagship missions, not something we expected to get around the nearest Sun-like star this early. That's why S1, even as a candidate, is taken so seriously. It's not just, hey, maybe a planet, it's, we're already fighting at the level of contrast we thought was 10 or 20 years away for this specific system. Now look at the separation game. At 4.37 light years, 1 astronomical unit corresponds to about 0.76 arcseconds on the sky. So if a planet is orbiting between 1 and 2 AU, it will appear somewhere between about 0.8 and 1.5 arcseconds from the star. On paper, JWST's 21-foot, 6.5-meter mirror can resolve that easily in the mid-infrared. The raw angular resolution is not the problem. The challenge is doing that while keeping the wavefront, the exact shape of the light coming through the telescope, stable enough that the chronograph can work properly. Every tiny vibration, every small temperature shift, every slight misalignment changes the pattern of residual starlight left after the chronograph. When you're trying to see something that faint, those changes matter. That's why the observatory has to be ultra-stable, why there's so much effort on wavefront control, and why the chronograph alignment and calibration are borderline obsessive. This whole exercise is a preview of what the next generation of planet imagers will have to handle when they go after Earth-radius planets at one astronomical unit around Sun-like stars 30 to 50 light-years away. There, the angular separations will be smaller, the planets fainter, and the stability requirements even harsher. SE1 is basically the easy mode version, and even that's brutal. Then you have the part of the problem that manufactures fake planets for a living, speckles. Every tiny imperfection in the optics, surface roughness, alignment errors, tiny wavefront ripples, throws off little bright and dark spots in the image. Those speckles are fixed to the telescope's optical system, not to the actual sky, but in a single exposure they can look exactly like a point source. They're the reason you can't just point, see a dot and yell planet. To fight that, astronomers use tricks like roll subtraction. You rotate the whole telescope by some angle, take another image and compare. Real objects in the sky move around the star when you rotate, because their positions are tied to the sky. Speckles, which are tied to the optics, stay put relative to the detector. Subtracting images at different rolls lets you cancel out a lot of speckles while keeping real sources. The catch for S1 is simple and annoying. In 2024, JWST only had one usable roll angle for that dataset. There wasn't a full set of rotated views to run the strongest possible speckle rejection tests. So you see a clean point source, but you can't absolutely hammer down the question, is this moving like a real object or sitting like a speckle within that single epoch? That's exactly why the community keeps using the word candidate. The data are strong enough to be exciting, but not strong enough to skip the skepticism. Here's the key thing though, even if S1 turns out to be some exotic artifact we don't fully understand yet, this whole effort is not a loss. In the worst case scenario, where later observations never find the planet again and the field gradually agrees, okay, that first detection was a clever illusion, we still learned that JWST's Mirai coronagraph can actually operate at these insane contrast levels around the nearest Sun-like star. We still get the strongest limits ever on dust and giant planets in Alpha Centauri A's habitable zone. We still walk away knowing that any Saturn mass planets brighter than a certain level in certain orbits are ruled out. That information alone is valuable for mission design and for our picture of the system. But if S1 holds up, if future JWST campaigns, radial velocity pushes, or even next-generation direct imagers see a consistent signal where the models say it should be, then this becomes something much bigger. It means we've already demonstrated the key technology for imaging gas giants in habitable zones around Sun-like stars right in our backyard. From there, scaling down to smaller, cooler, Earth-sized planets is a question of mirror size, stability, wavelength, and time, not a question of is this even possible. In other words, S1 is the line in the sand. Either it teaches us how easy it is to fool ourselves at extreme contrast, or it proves that we're already living in the era where directly imaging habitable zone giants and eventually potentially habitable worlds is not science fiction but standard practice. And if a Saturn-class planet in the habitable zone of the nearest Sun-like star is already pushing our instruments this hard, what happens if that planet also comes with a family of large moons, some of which might sit in the sweet spot for atmospheres and liquid water? And how close are we really to detecting anything like a real-life Pandora in a system only 4.37 light-years away? How do you talk seriously about a real Pandora when you can't even say for sure the planet is real yet? The only honest way is to start with the physics and work forward. If S1 exists as a Saturn mass gas giant at 1 to 2 astronomical units from Alpha Centauri A, then right away it has the potential to be a moon factory. A planet that, massive in that orbit, has what's called a Hill sphere, a region where its gravity dominates over the stars and where moons can orbit stably for billions of years. For a Saturn-class planet in that position, that stable region stretches out to tens of planetary radii, which means hundreds of thousands to millions of miles, comfortably bigger than Saturn's moon system today, which reaches out to Titan at around 759,000 miles, about 1.2 million kilometers. So from basic orbital mechanics, there's no barrier to S1 having multiple moons, some of them large. We already know nature can build big moons. Look at Ganymede and Titan in our own solar system. Scale that up a bit, put it around a slightly more massive gas giant in a warmer orbit, and you can absolutely imagine a stack of satellites from tiny icy rocks up to Mars-sized bodies, or even bigger. The open question isn't can such moons exist, it's did this particular system actually build them, and did they survive whatever chaos S1 went through to end up on its current orbit? If you want to talk about habitability in any serious way, you have to ask, how big does a moon around S1 need to be before we can even start thinking about atmospheres and liquid water? There are some rough benchmarks. First, radius. In general, you want something at least around 1,500 to 2,000 miles in radius, roughly 2,400 to 3,200 kilometers, to hold a thick atmosphere over billions of years without losing it to space. Second, internal heat. You need a mix of energy from radioactive decay in the interior and from tidal flexing as the moon orbits the giant planet. That heat drives volcanism, keeps a core molten, and helps recycle material through the crust. Third, gravity. You need enough mass to retain water and possibly run plate tectonics, which helps regulate climate over long timescales. A Mars-sized moon with a radius around 2,100 miles, about 3,400 kilometers, parked in a stable orbit around S1 at roughly 1.5 astronomical units from Alpha Centauri A, hits those basic marks on paper. It would get close to Earth like sunlight, it could have enough gravity to hold an atmosphere, and tidal heating from SE1's gravity could keep its interior active. If the composition is right, the atmosphere is thick enough, and there's some kind of magnetic field to help protect it from stellar wind, you could end up with surface conditions that are at least in the same broad category as Earth-like. That doesn't mean blue forests and floating mountains, it just means liquid water and a stable climate are not crazy. But then you hit the brutal detection wall. If S1 is hard to see, its moons are basically invisible to us right now. JWST is barely pulling the planet's own thermal glow out of the noise in the mid-infrared. Any moon would be much smaller and colder, and its light would be orders of magnitude dimmer. In thermal light, it would be buried under the combined glow of the planet and the remaining noise from the star. In reflected light, at visible wavelengths, a moon's signal would blur into the planet's point spread function, just a tiny perturbation on top of an already tiny signal. Could we try tricks like transit timing variations, watching tiny changes in the timing of S1 crossing in front of the star to infer a moon? In theory, yes. In practice, not now. We don't even have confirmed transits of S1. The orbit is tilted, the system geometry is awkward, and Alpha Centauri A is a difficult target for that method. At this distance and with the current technology, transit-based exomoon detection in this system is basically off the table. So you're left with this uncomfortable reality. The kind of instruments that could clearly resolve a moon around S1 are post-JWST telescopes, maybe large, dedicated direct imaging missions with extreme coronagraphs, or even kilometre-scale interferometers in space that combine the light from multiple mirrors across big baselines. Those are concepts people talk about for the second half of this century, not tools we have now. This is exactly why scientists get very careful, very fast when the real-life Pandora angle comes up. Popular articles love that phrase, it's an easy headline, but if you look at what the researchers actually say, they almost always repeat the same set of qualifiers. First, we don't even know if S1 is definitely a planet. Right now, it is a candidate based on a single strong detection, a possible connection to an older hint from near, and orbital models that fit the non-detections. That's not nothing, but it is not proof. Second, we have zero direct evidence for any moons. Not one photon has been clearly attributed to a satellite in this system. Everything about exomoons here is built on if S1 is real, and if it has moons, and if they are big enough. Third, big Mars-sized exomoons might not be common. We don't yet have a strong statistical sample, but the few candidates we've seen hints of in other systems suggest that really large moons are rare outcomes, not guaranteed features of every gas giant. The formation pathways that build such satellites may require fine-tuned conditions in the circumplanetary disk, and the later dynamical history and scattering migration interactions with other planets can easily strip moons away or crash them into the planet. In a tight dynamic system like Alpha Centauri A, we simply don't know how forgiving that history has been. That tension between how wild the potential is and how thin the hard evidence still is the whole point. 4 light-years away, there might be a Saturn-class planet in the habitable zone with a family of interesting moons, or there might not be. We're at the stage where even confirming the planet is a major challenge. Which leads to the next uncomfortable but crucial question. Even if S1 and any moons are there, could we ever actually go there with real hardware, or are we locked into watching this system from afar forever? How do you take something that's 25.6 trillion miles, 41.2 trillion kilometers, away and turn it from nice telescope target into place we actually visit? The first thing you have to admit is that everything we've flown so far is basically standing still on that scale. Alpha Centauri sits at about 4.37 light-years. Voyager 1, the fastest and farthest human-made object right now, is moving at roughly 38,000 miles per hour, 61,000 kilometers per hour. If you took that speed and just pointed it straight at Alpha Centauri, no fancy maneuvers, no slowing down, you'd be looking at something like 70,000 to 100,000 years of travel time. That's longer than human civilization has existed. So with today's chemical rockets, the answer is simple and brutal. You do not go to S1. You don't go to Alpha Centauri at all. You watch from here. So if chemical rockets are basically dead on arrival for interstellar distances, what's the next step up that isn't pure fantasy? This is where ideas like Breakthrough Starshot come in. The basic plan is aggressive but not magic. Instead of launching a huge ship with fuel, you launch gram-scale probes attached to ultra-thin light sails. Those sails are only a few microns thick, but spread tens to hundreds of meters across. Back home in the solar system, you build a multi-gigawatt laser array, and you hammer those sails with focused light. The push from the photons over a few minutes drives the sail up to around 20% of the speed of light. At that speed, you turn the Alpha Centauri problem from geological timescale into human lifetime timescale. A probe cruising at 20% light speed would cross the 4.37 light-year gap in about 20 years. Then you add the roughly 4.4 years it takes for a radio signal to travel back, and you're looking at data return less than 25 years after launch. The payloads on those sails are tiny, basically chips, miniaturized cameras, spectrometers, communication systems, but in principle they could grab snapshots, spectra, and basic environmental data as they tear through the target system. That sounds perfect until you hit the next problem, and it's a big one. These missions are flybys. You're screaming through the Alpha Centauri system in hours to maybe a couple of days. There's no slowing down, no orbit, no second pass. At 20% of light speed, you don't have time to stop, you barely have time to blink. So if you want a probe to actually hang around, take its time, orbit S1, look for the moons, maybe even drop secondary payloads, you need a way to brake. That's where the really tricky concepts start. The leading serious idea on the table for slowing down a sail-based probe is something called photogravitational braking. Instead of just firing a laser at the sail from behind and letting it coast forever, you design the mission so that the sail arrives at Alpha Centauri with its reflective side facing the stars. Then you use the combined radiation pressure from Alpha Centauri A, B and Proxima, plus their gravity, to slow the sail down as it swings around the system. You basically surf the light and gravity fields to bleed off speed. Models suggest that if you build sails with very low mass and very high area, and you accept lower cruise speeds, around 4 to 5% of the speed of light instead of 20%, you can do this. The travel time goes up. You're now talking roughly 95 years to reach Alpha Centauri A, and then another approximately 46 years to reach Proxima on a second leg. But in exchange, you don't just blast through, you actually capture into bound orbits. That gives you years to map the system, fly by S1 repeatedly, and maybe deploy even smaller sub-satellites into local orbits. It's not fast in human terms, but in interstellar terms it's shockingly practical, within a couple of long lifetimes, instead of never. So where does S1 fit into this? Why does one Saturn-class gas giant matter enough to change how you design a mission that takes a century? The answer is, it changes the goal from vague to specific. If the nearest Sun-like star definitely has a gas giant in the habitable zone, then you're not just sending a probe to check out Alpha Centauri and see what's there. You're sending it to a known named target. S1 becomes the anchor point for the entire mission profile. First, S1 would be a bright infrared luminous target for a flyby. A gas giant at 225 Kelvin is glowing in the mid-infrared. Even a tiny chip-sized imager could grab detailed thermal maps, measure cloud structures, and watch how its atmosphere behaves as the probe races past. Second, S1's gravity well gives you options. A gas giant is a great place to use gravity assists, tweak trajectories, and test out capture orbits for smaller daughter probes. Third, if there are exomoons or Trojan companions sharing its orbit, S1's neighbourhood becomes the prime hunting ground for complex environment worlds. You focus your highest resolution imaging, your best spectrometers, and your longest dwell times on that region. This is why S1, if confirmed, doesn't just tweak the science case. It rewrites the mission brief. Without S1, an interstellar mission proposal looks like, let's go to the nearest star system and see whatever we can see, maybe there are planets. With S1 confirmed, the language shifts to, we are going to the Saturn-class planet in the habitable zone of Alpha Centauri A, and we will map its atmosphere, search for moons, and profile the entire system architecture. That kind of concrete target makes it much easier to argue for the cost, complexity, and timescale of a true interstellar project. Funders and agencies are much more likely to back a mission when you can point at a specific world and say, we're going there. So you have this weird split. On one side, the physics of distance is still brutal. Even with light sails and clever braking, you're talking about decades to a century. On the other side, if S1 is real, it gives humanity a clear bullseye in the nearest star system, a world that's big, bright in the infrared, sitting in the habitable zone, and massive enough to be the hub for anything we send there. Which leads to the next step in the story. Even before you think about going physically, how do we actually lock this planet down from here? What are the concrete steps for turning S1 from candidate into confirmed, and what tools on the ground and in space have to line up for that to happen? So how do you actually move S1 from maybe to yes, this is a real planet? The basic answer is you stack methods. You don't trust any single technique, you make them all agree. The first and most direct step is simply more JWST time. That's the straightest path in front of us. You take the best fit orbits that connect C1 in 2019 and S1 in 2024, you project them forward, and you mark the spots in the sky where S1 should be in 2026 and 2027 at specific dates and roll angles. Then you go back to MIRI with the coronagraph. You run the same kind of observing sequence, and you look for a point source with the same brightness and colour at roughly the predicted separation and position angle. If that point shows up again, where orbital physics says it should, that's basically the smoking gun. One detection could be a fluke. Two detections years apart lining up on a single orbit are not. You'd be able to say this thing moves with the star, it has a consistent brightness and spectrum, and it follows a bound orbit, which is exactly what you want for a confirmed planet. If nothing shows up at any of those predicted positions, even in the best sensitivity zones, that would push hard in the other direction toward the 2024 signal was an artifact. So the first big confirmation step is really just a high-stakes calendar game with JWST. Get the time, hit the right windows, and see if the dot returns. While that's happening, you don't just sit around, you keep hammering Alpha Centauri A from the ground with radial velocity. RV is the method where you watch the star's spectrum shift back and forth as planets tug on it, changing its line of sight speed by a tiny amount. A Saturn mass planet at 1 to 2 astronomical units induces a wobble on the order of a few feet per second, around 1 meter per second. That's small, but not crazy small. The problem is that Alpha Centauri A is bright, active, and part of a binary. The gravitational pull from Alpha Centauri B and the star's own noise sit on top of that tiny planetary signal. Current state-of-the-art spectrographs on large telescopes are just about at the edge of being able to see a 1 meter per second signal cleanly, and that's in nice, isolated stars, not a tight binary. So the community is pushing hard here. Longer baselines, better modelling of stellar activity, better treatment of the binary motion. What you want is a long-term RV trend with a clear 2 to 3 year period that lines up with the orbit implied by C1 and S1. Even if the signal is barely above the noise, seeing a consistent wobble with the right amplitude and period would be a powerful cross-check. It wouldn't replace JWST, but it would tell you there's something of about the right mass pulling on this star. On top of that, you have Astrometry, which are basically measuring how the star wiggles sideways on the sky over time. Instead of just looking at how fast the star is moving toward or away from you, you measure its tiny positional shifts as a planet drags it around a shared centre of mass. For a Saturn-class planet at about 2 astronomical units around Alpha Centauri A, that sideways wobble is incredibly small micro-arcseconds, but not zero. With dedicated space missions built for micro-arcsecond astrometry, you could, in principle, watch that slow tiny orbit of the star itself and infer the planet directly. Gaia is giving us a first taste of this kind of precision for many stars, but Alpha Centauri A is a tricky target. It's bright, and it has a companion star messing with the clean signal. So Gaia isn't the final word here. What you'd really want is a future mission aimed specifically at ultra-precise astrometry for nearby Sun-like stars, including Alpha Centauri. If such a mission flew and it measured a sideways wobble of Alpha Centauri A with the same period and amplitude as the RV and JWST orbit suggest, that would close the loop from a completely different angle. You'd have imaging, line-of-sight velocity, and skyplane motion all telling the same story. Finally, you bring in the next generation of direct imagers beyond JWST. The Nancy Grace Roman Space Telescope is the first big one in that line. Roman will carry an advanced coronagraph operating in visible and near-infrared wavelengths with extremely stable optics. Alpha Centauri. A plus S1 is exactly the kind of system Roman is designed to stress test. JWST sees S1, if it's real, in thermal light at mid-infrared wavelengths, where the planet is glowing with its own heat. Roman would come at it from the other side, looking for the planet's reflected starlight. If Roman can confirm a point source in visible or near IR at the same location where JWST sees S1 in mid-IR, you suddenly have a multi-wavelength picture. You can measure how bright the planet is at different wavelengths as it orbits, its phase curve, how its brightness changes as different sides are lit up. That feeds directly into constraints on clouds, atmospheric composition, and maybe even weather patterns. You're not just saying this is a gas giant, you're saying this is a gas giant with this kind of reflective cloud deck, this kind of thermal structure. And S1 becomes the first real boss-level challenge for the whole direct imaging roadmap. The object every new instrument has to prove itself on. Put all of that together, and the confirmation plan looks like this. JWST tries to catch S1 again in the 2026 to 2027. Ground-based RV keeps grinding away, hunting for a matching 2 to 3 year wobble at about 1 meter per second. Future astrometric missions try to see the sideways wiggle. Roman and later observatories try to nail down the reflected light, phase curves, and atmosphere. You don't need every method to work perfectly, but you do need multiple independent lines of evidence to line up. Only then do you move one from candidate to confirmed without hesitation. And once you do that, the story changes again. Because if the nearest Sun-like star really does host a Saturn mass gas giant in its habitable zone, on an eccentric inclined orbit, that's not just one interesting data point, It's a direct punch to a lot of our planet formation models. It forces you to ask, if this is what's sitting right next door, how many other sun-like stars are hiding similar giants in their habitable zones? And what does that do to the odds of smaller, Earth-like worlds forming and surviving in those systems? If the very first sun-like star next door turns out to have a Saturn-class planet sitting in its habitable zone, what does that say about the rest of the galaxy? That's the uncomfortable question S1 throws at planet formation models. For years, gas giants parked in temperate zones were seen as kind of oddballs, migration mistakes, edge cases. But if the closest G-type star to the Sun has one, that starts to look less like a rare accident and more like a normal outcome we just haven't been able to see until now. If S1 is real, you're basically forced to accept that a Saturn mass world at 1 to 2 astronomical units around a Sun-like star is not some crazy outlier. We didn't go looking at hundreds of stars and finally dig up a weird system 150 light years away. We pointed our best telescope at the nearest target and boom, there's a candidate. Statistically, that hints the underlying population of giant planets in or near the habitable zone could be large. Not every Sun-like star will have one, but the models that treat them as extremely rare suddenly look shaky. That means formation theories have to bend. You can't just say gas giants live beyond the snow line at 3 to 5 astronomical units. End of story. You have to make room for giants that either form there and survive closer in, or actually form in situ in a warmer region under certain conditions. You also have to make their migration histories less catastrophic because S1 has to end up in the habitable zone without completely wrecking every smaller world along the way. In other words, if the nearest G-type star has this setup, then your default mental picture of typical Sun-like planetary systems needs to shift to include habitable zones that can host big giants as well as Earth-sized worlds. Now add the fact that Alpha Centauri A is not alone. Alpha Centauri B is not some distant background star, it's a real gravitational partner, orbiting between about 11 and 35 astronomical units from A. That range takes it from roughly Saturn's distance from the Sun out to beyond Pluto's distance in our system. A companion like that does not politely sit back and ignore the protoplanetary disk. It truncates the disk, cutting it off at some outer radius. It stirs up the planet-building material, the planetesimals, making their orbits more eccentric and more inclined. Over millions of years, its gravity can drive migration and tilt through long-term, slow effects called secular perturbations. If S1 really sits on an inclined, eccentric orbit around Alpha Centauri A, it starts to look like a fossil record of all that early gravitational drama. The tilt tells you the plane of the planet's orbit was twisted relative to the main disk and the binary orbit. The eccentricity tells you its path was stretched, probably by interactions with the disk, with Alpha Centauri B, or with other planets that might have been kicked out or swallowed. S1 becomes a surviving witness, the one big body whose orbit still carries the imprint of the system's formation history. Instead of just modelling single star plus disk, you now have to model disk plus close stellar companion plus migrating giant, and make all of that end with a gas giant at 1 to 2 AU that stays stable for billions of years. To get a feel for how serious that is, compare it to what our own Jupiter and Saturn do. Jupiter orbits at about 5.2 AU, around 484 million miles, 778 million kilometers, from the Sun. Saturn orbits at about 9.5 astronomical units, roughly 886 million miles, 1,427 million kilometers out. Those two giants shape basically everything in the solar system. They shepherd and scatter asteroids, they set the boundaries and structure of the asteroid belt, they sculpt the Kuiper belt, and they act as partial shields, deflecting some comets away from the inner system while flinging others inward. Their positions and masses decide how many impactors Earth gets over billions of years and when. Now drop a Saturn mass planet into the 1 to 2 astronomical unit range instead, in a system like Alpha Centauri A. Suddenly the giant planet architecture is much more intimate with the habitable zone. S1 isn't sitting outside the region where Earth-like planets would live, it's embedded in it. That means any rocky worlds closer in or co-orbitals or large moons grow up under a much stronger, more immediate gravitational influence. ESSA-1 can enhance the delivery of water and volatiles by perturbing icy bodies from farther out, or it can destabilize smaller planets and clear them out. It can create gaps and resonances where only certain orbits are long-term stable. In practice, that could either help or hurt the chances of Earth-like worlds. On the plus side, a well-placed giant can protect inner planets from too many big impacts and help deliver water. On the minus side, a badly placed or migrating giant can eject forming Earths, smash them together too violently, or strip them of atmosphere. S1, living right in the habitable zone, is not just a background character, it's the main sculptor. If smaller rocky planets or big moons exist there, their current orbits, climates, and even their ability to hang on to atmospheres are all downstream of what S1 has been doing gravitationally for billions of years. Zoom out one more step and you see that S1 is just one more example in a growing list of habitable zone weirdness cases. Right next door, Proxima Centauri B is an Earth-mass planet in the habitable zone of a red dwarf, a star much cooler and smaller than the Sun, with flares and high-energy radiation that are totally different from what we get from a G-type star. Kepler and TESS have already shown us compact multi-planet systems where several super-Earths, or mini-Neptunes, pack into or near the habitable zone, sometimes with orbital periods of just a few weeks or months. Put Alpha Centauri A plus A possible S1 into that mix, and the pattern is clear. Habitable zones are not clean, single-lane highways with one neat solitary Earth in the middle. They're crowded, varied spaces. In some systems, they host chains of small rocky planets packed close. In others, you get one big gas giant plus room for moons and co-orbitals. In red dwarf systems, you might have tidally locked Earth-mass planets hugging very close to faint stars. The idea that habitable zone means one Earth clone in a circular orbit is gone. S1, if confirmed, becomes a key data point in that new picture. It says, yes, you can have a sun-like star, a close stellar companion, and a gas giant running laps right through the habitable zone, and the system can still be stable enough for billions of years. That pushes theory to handle a broader range of architectures and forces observers to think less in terms of find the one Earth, and more in terms of map the whole zone and see what mix of giants, rocks, and moons lives there. And that leads straight to the human side of this, because once you accept that the nearest sun-like star might have a big gas giant in the habitable zone, you're not just tweaking models, you're changing how people think about their actual neighbourhood in space and what kinds of missions, stories, and timelines we build around it. How different does your future look when nearest star stops being an empty label and turns into a place with a specific world you can point at? For most of your life, Alpha Centauri has probably been just a line in a book or a random fact you heard once. Closest star system, a few light years away, end of story. If S1 is confirmed, that changes completely. Suddenly you don't just have Alpha Centauri A as a concept, you have a particular planet in that system, with a mass range, a temperature, an orbit, and a story. It will get an official designation, almost certainly a shorter public nickname. And from then on, it's not some hypothetical planet out there. It's that world, 4 and a bit light years away, looping around a real star on a real 2-3 year track. That kind of concreteness matters more than it sounds. Once S1 is locked in, every interstellar mission concept presentation gets sharper. Instead of slides saying potential targets within 10 light years, you get a slide that says Alpha Centauri AB, or whatever its final name becomes, with an orbit diagram, expected phase angles, and instrument modes tailored to it. You can tell a specific story: bright sun-like star, Saturn-class gas giant in the habitable zone, probable history of migration, possible moons, potential inner rocky planets, all in one system just 25.6 trillion miles, 41.2 trillion kilometers away. That's a much easier pitch, both for scientists and for the public. It feels like picking a mountain to climb, not just pointing vaguely toward a range on the horizon. So what does that do to the way people feel about our neighbourhood in space? Even though S1 is a gas giant and not some perfect Earth twin, the psychological effect is not subtle. Right now, you can tell yourself that the nearest Sun-like star might be barren, or might have only small, hard-to-imagine worlds. If S1 is real, that picture is gone. You have to live with the fact that the closest G-type star to the Sun has a massive cloud-wrapped planet sitting in its temperate zone, glowing steadily in infrared, tugging on whatever smaller bodies orbit nearby. For human imagination, that's a big jump. You're not just thinking about maybe some rocky planets around some distant star 100 light-years away that we'll never visit. You're thinking a specific gas giant, almost in reach, with possible moons and maybe Trojans sharing its orbit. For funding agencies and policymakers, that also hits differently. A handful of radial velocity curves from a star 100 light-years away is an interesting graph. A confirmed, directly imaged gas giant in the habitable zone, 4 light-years away, is a headline, a destination, and a long-term goal all at once. It feels less abstract, more like something we are inevitably going to go after, even if that takes many decades. How does that emotional shift feed back into actual hardware? This is where roadmaps start to bend. With a confirmed S1, mission planning shifts from generic exoplanet observatories to systems we must be able to crack. Interferometric observatories, multiple telescopes in space working together as one giant virtual mirror, suddenly become easier to justify because you can say, if we build this, we can resolve moons and rings in the Alpha Centauri A system. Exomoon-focused designs go from fringe ideas to serious proposals because there is now a prime test case, a gas giant in the habitable zone only 4.37 light-years away. Dedicated Alpha Centauri missions, which right now sound like ambitious white papers, move closer to being possible flagship projects. You can imagine a sequence. First, a Roman-class or Louvois-class telescope that takes detailed spectra and maps the system from here. Then, in the late 21st or early 22nd century, an actual interstellar probe, laser-pushed sail or some other advanced design, whose official mission brief literally says characterize SWAN and its environment. That kind of long-range planning is much easier to build international coalitions around than a vague, go to another star someday. People rally around specifics. First mission to another star system with a known giant planet in its habitable zone. One becomes the anchor point, the thing your children and grandchildren see on posters and mission patches as the obvious next big leap after the outer planets and the Kuiper belt. But there's a catch here you can't ignore. What happens to all of that if S1 turns out not to be real? This is where there's a bigger lesson that goes beyond one planet. Science at the frontier is always walking that line between big, exciting claims and harsh reality checks. S1 is sitting exactly on that line. If the follow-up data in 2026 to 2027 and beyond repeatedly fail to find anything where the models say a planet should be, the community will, step by step, shift the consensus toward the 2024 detection was a very convincing, very educational false positive. That will sting. It will feel like losing a world you almost had. But if that happens, it will also be a visible demonstration of how seriously astronomers take self-correction. They won't keep the planet in the catalogue just because it's cool. They'll tear into the data, update the pipelines, refine the speckle models, and use S1 as a case study in how to not fool yourself at extreme contrast. That's not as glamorous as nearest gas giant confirmed, but it's just as important. It means the next time someone claims a planet right at the edge of what a telescope can see, you'll know the system that caught the mistake here is the same system filtering that future claim. On the other hand, if S1 reappears roughly where orbital mechanics says it should, with similar brightness and spectrum, the narrative flips in real time, and you will get to watch it happen. A dot that started as a suspicious blob in near data in 2019 became a disappearing planet in JWST images in 2024 and 2025, then comes back on schedule in 2026, or 2027 is about as clean a confirmation arc as you can get. You'd see papers, press releases, and probably live briefings walking through the updated orbit, mass, temperature, and environment. A planet 4 light-years away would go from rumour to reality in front of you over just a few years, and from that point on, every map of nearby planetary systems would carry its name by default. So you're in this odd place right now, where either outcome is big. Confirm S1, and you reshape how humanity thinks about its immediate neighbourhood and its long-term spaceflight goals. Lose S1, and you get a sharp demonstration of how careful you have to be when you push telescopes to their limits, and how robust the scientific process is at catching itself before it drifts into wishful thinking. Either way, you're not just a spectator, you're sitting at the exact moment when this call is being made. And that leads to the last piece of the story, which is about timing and perspective. Right now, teams are running simulations, planning observations, arguing over models, trying to figure out whether S1 is the first confirmed gas giant in the habitable zone of the nearest Sun-like star, or the most educational false alarm JWST has produced so far. The real question for you is, what does it mean to be alive while that decision is being hammered out, and how does that change the way you picture your place in the galaxy? Right now, while you're sitting here, people are literally running this system on supercomputers and trying to break it. They're taking Swan's possible orbit and pushing every dial they can reach. They nudge the eccentricity from 0.3 up to 0.5. They tilt the inclination by tens of degrees. They drop in different masses for the planet, different amounts of dust, different starting disk shapes. And they ask one simple question every time: what kind of system produces this and still matches the data we have? They track how the dust would evolve, where planetesimals would end up, whether a gas giant could really survive on that tilted, stretched path for billions of years without destabilizing everything. You're not reading about this decades later in a textbook. You're alive exactly at the moment when those simulations are being checked against fresh telescope data in almost real time. A run finishes, spits out synthetic images, and people compare them to the real JWST frames from 2024 and 2025. Does the fake planet land at 1.5 arc seconds? Does the dust come out too bright or too faint compared to what MIRI saw? Does the orbit put Swan in JWST's blind spots in 2025 the way the real non-detections did? This is not ancient history. This is right now while you're listening. So what do you do with that, beyond just thinking, cool, astronomy is busy? The simplest upgrade you can make is in your own mental sky map. Next time you see a chart of constellations, or you hear someone mention the southern sky, you don't have to let Alpha Centauri just be a label. In the constellation Centaurus, about 4.37 light-years away, there is very likely a Saturn-class gas giant looping around a Sun-like star every 2 to 3 years, cruising between about 1 and 2 astronomical units, roughly 93 to 186 million miles, 150 to 300 million kilometers out. JWST has probably already seen its heat once in that mid-infrared dot we've been talking about. Future telescopes will try to chase its reflected light, watch it brighten and fade as it orbits, and maybe one day an interstellar probe will fire past it and fly straight through its magnetosphere, sampling particles and fields directly. You don't need a fancy visual for that. Just hold the numbers in your head. 4 and a bit light years, Saturn-class, habitable zone on a stretched, tilted orbit. That's part of your neighbourhood now. The strange thing is, you're not heading toward one neat, clean outcome with this. You're walking toward 2 very different futures, and both of them are wild in their own way. In one future, S1 is confirmed. JWST catches it again around 2026 or 2027, maybe Roman or a next-gen ground-based telescope backs it up, and the orbit locks in. The disappearing planet becomes the closest gas giant in a habitable zone we've ever seen, and immediately turns into a cornerstone of exoplanet science. Every time someone talks about planet formation around Sun-like stars, S1 is in the first few slides. Every serious interstellar mission study has a section labelled Alpha Centauri A, S1 and possible moons. Textbooks change, outreach posters change, your idea of nearby space changes. In the other future, S1 evaporates under scrutiny. JWST looks again and again and nothing appears where it should. Radial velocity fails to show the right wobble. Future imagers never see a consistent signal. Gradually, paper by paper, talk by talk, the consensus shifts. The 2024 detection becomes the most instructive false alarm of JWST's early exoplanet work. People dig into the processing, refine the speckle models, maybe discover some subtle interaction between the coronagraph, the roll angle, and the binary nature of the system that nobody fully understood at first. That sounds like a letdown, but it's not a wasted branch. If S1 fails, we learn exactly how treacherous the edge of JWST's capabilities is. We find out where the pipelines can fool us. We get better at building instruments and algorithms that won't repeat the same mistake. The next time someone claims a planet at the edge of detectability, we'll have this entire saga as a cautionary template. Both futures are progress. One just comes with a Saturn mass trophy sitting 25.6 trillion miles, 41.2 trillion kilometers, away. So what do you actually do with this as a viewer? Besides wait for headlines, the key is to treat 2026 to 2027 as a real-world cliffhanger, not just a vague sometime later note. That's when JWST and probably a few other instruments will take their best shots at Alpha Centauri A again. When that happens, you're going to see a wave of papers, preprints, press releases, tweets, posts, videos, and yes, a ton of Alpha Centauri planet confirmed or disappearing planet debunked. Titles. It's going to be noisy. Your job, if you've watched this far, is to remember the context when that wave hits. Remember that S1 came from a single mid-infrared detection at about 3.5 millijanskis at roughly 1.5 arcseconds. Remember that it sat at a projected 2 astronomical units, with an estimated temperature of around 225 Kelvin, about -55 Fahrenheit, and a mass somewhere between 90 and 150 Earths. Remember that the orbit models had to connect that point to C1 in 2019 and also explain why 2025 saw nothing, giving about a 52% chance of S1 hiding in JWST's blind spots. If you keep those numbers and that logic in your head, you won't get whiplash when the next round of results drop. If the new data show a dot in the right place, you'll know why that matters. If they don't, you'll know why that hurts, but also why it doesn't mean the whole field is broken. You'll be able to tell the difference between hype and real confirmation, between possible planet and we have the orbit. And if S1 does turn out to be there, quietly circling Alpha Centauri A at about 1 to 2 astronomical units, then within your lifetime you're going to watch the language shift. People won't say if there's a gas giant around the nearest sun-like star. They'll just talk about our neighbouring gas giant in Alpha Centauri, the way we talk about Jupiter and Saturn now. It will be part of how kids learn the local cosmos. Sun, inner planets, outer planets, Kuiper belt, and then, 4 light-years away, a Saturn-class world in the habitable zone of the next star over. You're standing right at the split point between those futures. You're not late to the story, you're in the middle of it. The telescopes are running, the simulations are running, and the clock to the re-observation window is ticking. All you have to do is remember what you've just learned, and pay attention when Alpha Centauri A comes back into the news. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.